continuous random variables, and these are, a lot of this stuff is just general probability. It's not related directly to electrical and computer engineering. So, all right, so what I wanted to do is first mention something. When we're talking about how, if you have n items and you've taken k at a time, the two things that can happen, one are permutations, the other are combinations. All right, so for instance, if you have n items and you've taken k at a time, so we have n items, we're taking them k at a time, and we're talking, the order is important. Follow me on this? So just think if we have A, B, C, D, E, F, G, we'll do an example of this, and you want to take 4 of those letters, and the order is important, like A, B, C, D would be different than D, C, B, A. Order is important. These are called permutations. And when you have that, the symbol is usually N, capital P of K. And what that means is, and I'll try to explain this in a simple way. In his book, he does this. He says if we have n items and we're taking k at a time, the first item could be n. That should, any of them, right? All right, now there's n minus 1 left. So the second one taken after that, and I'll tell you where this is in the book so you can look. If you haven't read this, please do. I spent some time last night going through some of this stuff, and I see why he's doing the way he's doing. This is on page 21. Right under, it's after the first paragraph. So then the next item would be, pardon me?
You're saying 27 of the book?
No, not
it's
yours.
21.
I thought, yeah, never mind, sorry.
It's what?
We were, he said 27.
No, it's in the old book. I thought he had the old book, so I was telling him.
Okay.
It's just 21, that's page 21.
You're correct.
All right. Anyway, so this would be the definition. I'll put it right here. This is going to be n times n minus 1. You have n items, you take one, n. There's n minus 1 left. That's the next ordered thing. Then n minus 2, dot, dot, dot. Finally, it's going to have n minus k plus 2 and n minus k plus 1, something like that. Now, this doesn't make a lot of sense to you until I write the equation down for it. What it really boils down to, this n p of k, the number of permutations, is really going to be, if you think about this, we go from n, and then we have, and I'll give you an example, there's k items, so we have n, n minus 1, n minus 2, n minus 3. Finally, we get all k items in there. And what we can actually do is say that's really n factorial, because that's what I'm doing here, divided by, and this is going to be n minus k factorial. Now, the reason for that is, if you have n factorial, you have n, n minus 1, n minus 2, n minus 3, all the way down the line. If you divide by n minus k factorial, down here you have n minus k minus 1, n minus k minus 2, and so forth, and you're left with just this bunch, you might say. So an example of this. Suppose I have, I did it with 3 and I did it with 4. All right, suppose I have the letters A, B, C, and D, and I want to see how many different combinations or permutations of those I can construct just taking 3 at a time. Do you all follow me? Not 4, 3. So the number of permutations of this would be n pk, or this is the first thing, so it's going to be n factorial. There are 4 items, and I'm taking them 3 at a time, so it's going to be 4 factorial over 4 minus 3 factorial. So that's 4 times 3 times 2 times 1 over, and this is just 1 factorial. So that's going to be, if you look at this, that's 12 times 2, or it's 24 different ways you can do it. Do y'all follow me in this class? How many cities, right? You can do it. I've done this. Last night I spent some time messing around with all this stuff. I generally don't deal with combinations and permutations with the stuff that I deal with radar. It's more involved with a continuous type of probabilistic approach where you have a continuous random variables, and you don't have this kind of thing. But it's good to get at least some feel for it, because there is a direct over or a direct parallel this with some of the continuous time stuff. You all follow me on this at least? All right. So, I mean, just as an example, how about we do 3 of 3? And I think I talked about this. If we have 3 items, say it's A, B, and C, and you want to take 3 at a time, how many different combinations? Well, it would be NP of K, and this would be 3 factorial over 3 minus 3 factorial, and this is 1 times 2 times 3, and this is 6, and that's exactly how many combinations you can get of that. We proved that. Agree with that? Now, if you don't care about the order, these are permutations, then we talk about combinations. And for combinations, this is the number of different ways you can take items where the subset is unique. In other words, it doesn't matter the order. It could be ABC, CBA, any of those things. That would be one set. So with combinations, this is the symbol he uses. We have n items and we're combining them k different ways, and we're taking them k at a time, the number of different ways we can take it. Follow me on this, class? So if we go back and we talk about the same problem, the first part where I have 4, I'm taking them 3 at a time. So for this one, the number of different combinations of that, we saw the number of different actually sequences, and it's when we have an ordered pairing of this is going to be 24. This is going to be equal to 4 combination 3, and the formula, I didn't put it down there, is n factorial over n minus k factorial times k factorial. So there's an additional term. It's the permutations divided by k factorial. With me, class? And we can prove that, but so we have n, which is 4 factorial, over n minus k, which is 1 factorial, times 3 factorial. And you can see it's 4. And if you actually do this, if we have A, B, C, and D, you could start out and pull off just the first 3, right? And then you would have A, B, C, and CBA, and B, A, C, and all those different things, all right? Then, if you look at this, I can have these 3, I can have these 3, right? That's 2. I can have these 2 and this one, 3, and then I can have these 2 and this one, 4 combinations. It's 4 possible things. And the set has the same actual values. Do you all follow me on this, class? So the difference between combinations and permutations, permutations has an ordering. In other words, like for the combinations, it doesn't matter the order these come in. For permutations, it does. That's the difference. That's it. Did you all try to read this stuff and go through it? It's a bit confusing. I spent a lot of time doing those problems. The wording sometimes took time to interpret. All right, now, with that in mind, what I'd like to do is do problem 31. Again, this is going to be, it's not really this applied, but it's generally introducing you to some of the concepts. Let me move back. And then we'll do 33. And I think I gave you 37, right? That's correct. We'll do them all. And we'll talk about it. This book, I noticed, is quite different than the other book because the other book, has anybody else seen that other book? You know what I'm talking about? Cooper and Millen or whatever it is. That book is Signals and Systems. Everything is related to electrical engineering aspects. Here, look at the problems. Breweries, coin tosses, it's everything but. Well, they did have chips in there, right? And they did have printers, so at least there's some similarity. All right, so for problem 31, it says, first of all, it's about a pin number. This is 131, and it says, if you have, you've got a card with a pin number on it, and so they want to know how many different unique, and this is only using numerics, so from 0 to 9 are the possible values of these. For 4 digits, how many different combinations or permutations right? So for this one, it's really going to be from 000 all the way up to 999, or there's 10,000. So here we have 10,000, 10 to the 4th different possibilities. We did that on Friday. That should make sense to you, right? The next part is what? He says if you discount for anything that's sequentially, and I put this on OneNote, anything that's a sequence like 1, 2, 3, 4, 2, 3, 4, 5, on all those things, you've got to discount that. And you were right about, your instincts were right about this. So you could have n as the first digit, then n plus 1 is the next digit, n plus 2, and then n plus 3. And if you count this, it started out with 0, right? You got 0, 1, 2, 3, then 1, 2, 3, 4, right? Then 2, 3, 4, 5, and you go all the way to down, and you're going to get 7 values here. This isn't directly related to the theorems he talked about before, but you all follow me in that? But you can also count backwards, would be basically you could have 7, 6, 5, 4. That would be another 7 values, right? So that's a total of 14 values here that we have to account for. And that's just in the sequencing, right? Do y'all remember that? Now there's one other thing. He says he wants to get rid of all things that have the same digit, like 1, 1, 1, 1, or start with 0, 0, 0, 0, 0, 1, 1, 1, 1, 2, 2, 2. So there's 10 of those. Does that make sense? All the way down? 2, 2, 2, 3, 3, 3, 4, 4, 4. There's 10 of them. So now we have another 10 values to get to include or account for. Then after that, he says he doesn't want anything that has 19 blank, because it could be your birth year. With me on this, class? So that's 100 possible values, 1900 all the way up to really 1999, right? So that's 100 values. I think I put the solution of this one on OneNote, I think.
Yes, you did.
All right, so that's basically all the values you have to account for. And I think in the question he says, how many different combinations are left? Is that what he says? All right, so for this one, it's pretty straightforward. The number of combinations left, I call this N1, is going to be really 10 to the 4th minus 100 minus 10 minus 14. So this is, what is that? 9, 8, I think it's 7, 6, isn't it? Is that right?
Yes.
Okay, that's the number left. Now, what's the next part of the problem?
Someone has stolen an ATM card and it's the first and last digits.
So this guy steals an ATM card. This is almost sounds like something. I got a story about ATMs in general later, but and what happened long ago. They let MIT people add an ATM to see if they could break in. What a mistake. Anyway, so here's 4 digits, and he says he knows the first is a 1 and the last is an 8, right?
First is 8.
First is, okay. So he knows it's 8, and he knows this is 1. Is that right? Okay. And then he says, if you know that, how many different, or what is the probability if he gets 3 guesses of guessing it right? Isn't that right?
With the restrictions of B.
Yeah. In other words, the guy, if he's smart, can discount things. So if there is a 1 there, right? He could discount all the. Basically, he could get rid of the. Whatchamacallit? Yeah, the 19 stuff, right? And so anyway, for this one, if you think about it, now just look at these 2 digits. If he has 8 and 1, are any of those being restricted? Well, if it was 8888, it would be a restriction, right? But it's not, correct? Mm-hmm. And it can't go 8, 9, 0, because you can't count past the breaks, the natural breaks at 0 and 10 or 9. Follow me? You with me on this, everyone? Because that's at least what's implied in the problem. So if you look at this, how many different combinations are there from 0, 0 to 9, 9? Do you agree? Or 100? That means the chances of him guessing right, and I checked the solution, this is right. Guessing right, if there's just 2 digits, there's 100 possible values. Do you agree with that, class? From 0, 0, 0 to 9, 9. For him guessing these 2 the first time would be 1 over, really it's going to be over 100, right? But he gets 3 guesses. Do you all agree? So that's just 3 over 100 if he gets that many guesses. Correct, class? Think about this. The pool of numbers that could be there are from 0, 0, 0 to 99, or there's 100 numbers. he gets 3 shots at it. So he's got, out of that space, he has 3 of the spaces that he's going to get right divided by the total number of 100. So it's basically 3 out of 100. Do y'all agree with this? I think that's the answer to it. All right, what's the next part?
Just have to recalculate the probability and see if the first and last digits are 1 and 1.
Or what?
Are 1 and 1.
Oh,
Just redo
all right,
that.
so now he's saying this. Remember, all these restrictions apply, correct? So now we have 1 blank blank 1, right? What happens now? What else? Remember, there were 100 possible originally, right? But what's discounted? The 1, 1, right? So instead of 100, now we have the top total possible. We have 100 minus 1. What else?
The 19.
19s, correct, class? So it's going to be minus
10.
what?
It'll be 10. Another 10, yeah.
Pardon me?
Would it only be 10?
Yeah.
For this one, it's going to be
902.
9, 0, right? 9, 1, 9, 2, 9, 3, 9, 4, 9, 5, and all the way down to 9, 9, or 10. Isn't that right? Correct?
Yes.
So it's going to be that minus 10, and that's going to be what? 89, correct?
Yes.
So if he gets 3 guesses in that one?
Yes, sir.
All right. So that means, all right, the first, obviously, if 1 guess, it's going to be 1 out of 89. 3, if he gets 3 guesses, it's 389. 3 out of 89 is the possibility he guesses right. Do y'all agree with that? Is that right, by the way?
Yes, sir.
All right. Is there another part to that?
And that was it.
Thank God. I can't, I get interested in this sometimes when it deals with cards, because long ago, I would watch this Poker After Dark thing. Have you ever, you know what this is? Have you ever heard this? Or it's a Texas Hold'em kind of poker, and all the probability of getting cards drawn, if it's a fair deck and a fair shot, is probabilistic, and without reading anybody, the probability of your hand being better than anybody else's, you can calculate, mathematically accurate. All right? You can do that because you know all the possible hands available. And then there's something called an expected return on a bet. And we're going to get, this is really, I'm kind of interested in this, because an expected payoff has a lot to do with radar and the expected ability to identify threats. And it's a different world, but in the world I live in, this is a direct application to some of the stuff I do. I started watching this and I realized that's part of the game. The other part is looking at your opponent and try to figure out by the way he's squirming what cards he has, but that's another story. A lot of that stuff I got interested in. Yeah.
Have you ever been to Vegas?
No.
I bet you'd be pretty good at it.
Huh?
I bet you'd be pretty good.
No, I wouldn't be. That's the thing, because I can't read people. My wife can, but I can't. She can read me like a book. She knows exactly what I'm thinking. If you're married, you probably know what I mean. Or if you got a serious girlfriend, because they can tell when you want to go fishing or want to get a pizza or something that they feel is wrong. Okay, next one is 33. Let's do that. Hold on. Let me just make sure. Okay. Is this the one? Oh, this is the one. Yeah, this one I understand. And I don't have to do this. So, how many did this problem? I think it's 3 different wines. Isn't it all red wines? Zinfandel, Merlot, and Cabernet Sauvignon. All right, so wines I've drank. Things I can relate. Okay, so give me this. He has 8 bottles of wine. Cab or something, or Merlot?
No,
Zin?
8 bottles of Zinfandel.
All right, good. And 10 bottles of what?
Merlot.
Merlot.
Whatever that is.
And 12 bottles of
Cabernet.
of Cab. All right. So we got, what is that? That's 30 bottles of wine. Starting to sound better and better. All right. 30 bottles of wine. And then the question is, so first thing we're going to figure out, if you just have 30 bottles, that's the value of n. That's the number n that we think about as possible things we can pick from, all right? Now, he says, I think it's 6 at a time, is that right?
Yes, sir.
If you pick 6 of them, what is the possibility of having so much of each, right? So the first thing you have to do if you're doing this kind of problem is figure out how many different ways you can pick 6 without ordering. You hear me on this? So these would be combinations. So the number of different ways out of 30 items that we can pick 6 would be 30 combination of 6. Now remember, this is a combination, not a permutation. With me? So order is not important to me. So that's going to be 30 factorial over 30 minus 6 factorial. And it's got to be divided by 6 factorial. Do you all agree with this? I remember, did I put a solution for this up or not?
Yes.
I think I put it in, I put the whole thing down in a separate, on OneNote, a separate one. And I mean, it's all like, it's one long spiel that's written out. But it's good, because it shows exactly what's going on. It's a little wordy. All right, for this one, what do we get? So 30 over 30 minus 6 factorial. By the way, when I started doing these on my computer, large factorials, it would just default and say it's over a certain value, you can't do it. And here's a trick to this. If you look at this, this is really what? 30 factorial over, this is going to be 24 factorial, isn't it? 24 factorial, 6 factorial. Now if I do this, that means really I have 30 times 29 times 28 times 27 times 26, if you want to do it this way, times 25, and then this one kills all the rest. Do y'all follow me? I have that, and then I can divide this by 6 factorial, which is 1 times 2 times 3 times 4 times 5 times 6. And in case you run into large number values for the factorial and your program, either MATLAB or whatever it is, gives you an error, this is the way you can beat that thing. So, does anybody have this one? Do you have?
193,775.
193,000, go ahead.
775.
I did this on my, I did it on my calculator, I mean on my laptop with MathCAD, and I use MathCAD a lot, or MATLAB or Oculus, but preferably I use MathCAD for other reasons. So that's the number of possibilities. Now, what is the question?
We actually skipped part A. It's if she wants to serve 3 bottles of Zinfandel, and the serving is important, we can use the concept of her fill.
Wait. She wants 3 bottles of Zinfandel? I'm just showing you, this is the number of different ways we can take 6 bottles.
Yeah.
That's it. Now, with her, what does she want now?
This was before that one. It says if she wants to serve 3 bottles of Zinfandel and serving order is important, how many ways are there to do this? It's a basic.
Okay, so how many ways are there to serve the Zinfandel, right? And order is important. The only thing we have to worry about is this.
And she wants 3 bottles.
And we want only 3 bottles. They're just looking for the sheer numbers here. You all follow me? The rest of this stuff doesn't matter. So how many different ways? Well, this is going to be a permutation. It's a permutation of 8 total, and this is going to be 3, taken 3 at a time. How many different sequences? So that's going to be 8 factorial over 8 minus 3 factorial, and that really is what? 336. Is that right? I think I put this, just before I came today, I put it in that, what is it, OneNote thing? It's up there, right?
You have it in there, that's correct.
Y'all follow me?
Yeah.
I think that's in the, is it in the solutions too?
Yes.
Okay. So that's the number, and that's just, you ignore everything else. Now what's the next part?
Use what you just did. That was the
But what's the next part?
total.
It's if 6 bottles are randomly selected, how many ways are there to obtain 2 bottles of each variety?
Okay, so this gets interesting. Now we know how many different ways we can get 3 bottles, right? Of Zinfandel. Now it wants 2 of each, right? Correct? So look, does it want the probability?
Yes, sir.
Okay, so follow me on this. This is the total number of different possibilities of taking these things, 6 at a time, correct? Now what we have to do is find what is the number of ways we can take 2 bottles. Is Zinfandel, is order important or not?
No.
No, not important. 2 bottles of Zinfandel, 2 bottles of Merlot, and 2 bottles of Cab. You all with me on this class? So here's what we do. For this part, is that part C?
Yes, sir.
All right, so now we want the probability of getting 2 bottles of each. Probability of just 2, 2, 2 for the numbers. So downstairs it's this. So that's going to be I'll just put it as 30 combination 6. That's a combination of how many different ways we can take 6 bottles from 30 total. Then up here, 2 bottles of Zinfandel, it's not ordered, so for 2 bottles of Zinfandel, it's gonna be 2, and this is gonna be a combination, or sorry, how many Zinfandels? 8, right? So this is gonna be 8 combination 2 plus, and then it's gonna be 10 combination 2 plus 12 combination 2. I'll write it over here, but I want to put it down. These are combinations, not permutations, because orders, yeah.
Should they be multiplied or added?
I believe they're added, right?
They're
Is it and?
Huh?
they're multiplied.
I think they should be multiplied.
Wait a second. Let me just be careful about this. Oh, yeah, they're disjoint. Probability of A times probability of B. I'm sorry about that, you're absolutely right. This is multiplied because these are disjoint. This and this are mutually exclusive, this and this and this and this are mutually exclusive. So the probability is going to be multiplied. And let me just say this to bring it back. When you talk about probability of A, all right, and this is going to be A, and this is a, well, intersect B, is probability of A, well, actually, let me write it this way. The probability of A given B is probability of A intersect B over probability of B as such, and there is no intersection. So they would be multiplied. Let me just take a look at this. I'm just trying to think of this in terms of sets. So all possible values, 2 right here, 2 right here. All right, if they're all disjoint, then it is multiplicative because there is no overlap. These are disjoint, so it would be that. Anyway, I believe that's right. Is that the right answer, by the way? They are disjoint, so that's right, it's multiplied. I'm sorry about that. When I do this, I'm going to get, over here, I get 30 factorial, this is going to be a strange number, over 30 minus 6 factorial over 6 factorial, then on top, I get 8 factorial over 6 factorial, 2 factorial, times 10 factorial over 10 minus 2 factorial, 2 factorial, and then 12 factorial over 12 minus 2 factorial, 2 factorial. And that should be correct, I think. So that's that number, 593,775 divided into all this.
It's 83,160.
What is?
The answer.
No, this is probability, isn't it?
D is the
This is
probability.
just like after
No,
part.
yeah, my bad.
So
Well,
it's-
wait, did they just, what did they ask for? This?
I mean, this is actually for probability.
How many possibilities? Read that again.
How many combinations for that?
How many ways are there to
Yeah.
obtain?
Oh, then it is
2 bottles?
multiplicative, yeah. So it's this times that times that. What was it?
83,160.
83,000, what is it?
160.
All right, that's the number of different combinations here that can occur. And I'm sorry about that, but what it really amounts to is the combinations that occur in the first one times the second one times the third. And the ordering is not important, right?
No.
Okay, so that's right. What's the next part?
It's a probability, which is just a part you do.
So it's this divided by, it's the probability of that event occurring. So the probability of getting, this is what I should have had, 2, 2, and 2, is going to be whatever that is, 83,160, divided by the total number, 593, 775. And what is that?
0.14.
0.4 what?
14. Oh, 1.4 to 0.4.
1.4.
14%.
All right, I got to tell you one other thing about this. The way I was doing it last night is I try to put down, in some way, shape, or form, sort of a visual image of all possible things that could occur. And that's what this is. If you think about, that's all possible things that can occur for taking 6 at a time. Then if you look at the subsets of these things, and you look at the numbers of this, this, and this, they all appear in that all possible things. I try to do this. And because these are disjoint, you're going to get this multiplicative thing. It'll be multiplied. All right, what's the next part? Sorry, stumbling question.
If it wasn't disjoint, you would just add them?
No, well, here's, if it's conditional probability and there's overlap, and like, you see, if, this would be something, I'm going to try to say this, if the order was important, it would be different. I'm trying to say this in a way that's meaningful to you, but these, the probability of, I mean, if you take 2 at a time of these things, of each, of 2 at a time, what's the probability of getting 2 of each? The way you'd have to look at this is you'd have to say that of all these things, you'd start going down and you'd list, like Zinfandel, Merlot, 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 Merlot. You would go through every possible combination that could occur. Now, if there was some combinations that were dependent on others, then there would be overlap, and it would be conditional probability. And I'm not saying it well, but we'll get to that. Sorry, my language is a little more geared towards things related to radar, not bottles of wine, but I hope you can appreciate this. If you look at the total number of possibilities, and you just think of all the possibilities that have 2 Zinfandel, 2 Merlot, 2 Cabaret, this will be the right answer for that, if you do it right. Okay, go ahead.
If 6 bottles are randomly selected, what is the probability that all of them are the same variety?
All right, so this is kind of interesting. First, it's probabilistic, right? So all the combinations of 6 are still that 53,000, whatever it was, that number, right? So the total number, n, is still going to be equal to 30 combination of 6, or 30 factorial over 24 factorial times 6 factorial. That's still going to be the number of possibilities for 6 bottles, right? Now, when you talk about the possibility of all of them being the same. So the first thing is, if we have 8 Zinfandel, the probability of getting all Zinfandel, 6 Zinfandel would be 8 combination 6. Order's not important, right? So that's going to be what? 8 factorial over 8 minus 6 factorial, 6 factorial. That's going to be the combination. Do you all agree with that, class? For 8 Merlots, it's going to be 10 combination 6, or it's going to be 10 factorial over 10 minus 6 factorial, 6 factorial. And then for the cab, 12 combination 6 is going to be 12 factorial over 12 minus 6 factorial, 6 factorial. Now we have all those things together. And by the way, these are separate, right? This is independent of this, is independent of this, correct? This should be additive, I believe. All right, so for this one, the probability of getting either all 6 cabs, 6 Merlot, or 6 Zinfandels should be this number, n, whatever that is, and this should be over these. So 8 combination 6, and I believe it's plus here, 10 combination 6 plus, and it's 12 combination 6, right? Because these are subsets that they're not overlapping there. Do you all agree with that? Is that the right answer, by the way? Sorry?
It Should be.
I mean, I have it there, don't I? What's the answer to this thing? Because we put that one that's 5,093, whatever it is, right? What does this come down to?
It's
So-
.002.
That's correct.
Is that right?
Yeah.
0.002, but each one of these is unique. If this occurs, right, it's separate from this, it's separate from this. We'll go through more of these, this will become a little clearer to you. The first one, it's an overlap. I mean, it's multiplied. It's multiplied because and that's what do they call that, the basic counting principle. I think we'll see this in a bit, a little better. But what's the last part?
That was the last
Was it? There's nothing out with it?
Yeah.
Oh, we got beer samplers then, right?
one. That's 37.
Yeah.
Liquor bar stops.
Okay. I hope you're getting a little appreciation for this. I don't know if there are Venn diagrams in the solution on this one, but they help. The problem is I'd have a hard time figuring out how to show all the combinations in a Venn diagram for that, for me. Okay, go ahead.
A local bar stocks 12 American beers, 8 Mexican.
12, this is beer. And this is 137, 12 American beers, they're domestic,
8 Mexican beers,
8 Mexican.
and 9 German.
All right, so what is it, 29 total? Total beers, go ahead.
You ask the bartender to pick out a 5 beer sampler for you.
Okay, so now we're just gonna figure out the number of different ways out of 29 things. Five, right? 5 can be taken, correct? Okay, so now we come down, and order is not important, so we're gonna have 29 combination of 5. This is the total number in different ways, 5 of them can be taken. So that's gonna be 29 factorial over 29 minus 5 factorial, 5 factorial. I think my computer can do this, the 29 factorial, I believe. But what is that number?
118755.
11855,
755.
that number?
This calculator can do it also.
Good. Is that right?
Yeah, it does.
Well, we need it though.
Yeah.
We're gonna need it. What's the next question? I mean, I need this before I do anything else. Okay, so that's taking 5 at a time. That's the number of different combinations, not permutations. Go ahead.
100,000, or no.
I think that's right.
Yeah.
Let's keep going. What's the next question?
What is the probability you get at least 4 American beers? And assume the bartender makes the 5 selections at random and without replacement.
All right, 4 American beers, right? So first, think about at least 4. So 4 or 5, right?
Yeah, at least 4.
All right, so for 4 American beers, looking just here, all right, that's gonna be 12 combination 4, or it's 12 factorial over 12 minus 4 factorial, 4 factorial. That's for 4 of them, right? But we can also get 5 of them. Do you agree with that? So it's 12 combination 5, and that's gonna be 12 factorial, 12 minus 5 factorial, 5 factorial. Those two things are correct, right?
Yeah.
And also, we have to account for what? The probability of getting
One of the, go ahead.
one, we gotta do this one. So we have a total of what? That's
17.
17 beers, right? So 17 total here. So we need to get,
17 choose one.
that's right, we have to get a permutation of 17 combination 1, and that's 17 factorial over 17 minus 1 factorial, or really just 17,
Yeah.
right? 17, and then we got,
You have to do 17 combination 0.
yeah, but that's just,
Just one.
that's 1, right? I mean, if we have combination, 0 is just 1. So then, let's see. So it's going to be this times that plus this times that, right? As the two that you have to account for the total. We want the probability, right? Probability of 4 American or more beers, and that's going to be N, I'll just leave it as N, and then it's going to be 17, I'll tell you what, I'm going to put this down, so it's going to be this. 17 combination 1 times 12 combination 4 and plus, and it's going to be really just 1, right? Times, and this is going to be 12 combination 5, correct? For that? All right, what is that? Because I don't know what these numbers are off the top of my head, but this is what?
It'll be, the answer will be 0.008C.
Is that right? So it's 0.82%? Is that right, class? Is the answers, did I put the answer for this one?
It was in the book. But I don't think you did the answers for this one.
This is 37, right? Hold on.
It's 0.77, 0.0775.
0.0,
775.
is that right? Class? All right. And, all right, so that's,
I was reading the next one, sorry.
all right, it's, these things get a little confusing. When I sit down and I'm doing these things, it's a lot easier than working on a board for some reason. I don't know why. The next part is what?
What is the probability you get 5 years from the same country?
Okay. So if you think about 5 beers from the same country, same country.
Same country, yes.
All right, well, you know, the total number, 29 combination 5 is still going to be N. We're going to need that for the probability. Y'all follow me? That's the total number of different 5 combinations. Now, 5 from each country, right? So if we had 5 from all American beers, it would be what? That would be 12 combination 5 would be the number of combinations to have all American beers. Do you all agree with that? Remember, this is the total number of combinations. This is one subset. Then there would be what? There would be 8 combination 5 for the Mexican beers, whatever this number is. This is good. I'll just put it as M. This is American. And finally, then it's going to be 9 combination 5, and this would be for German beers. Do you agree with this? Now, hear me on this one. This is all possible 5 combinations that accounts for every mixture of them. This is one subset of that number. Think of it this way. Here's N is the set S equal N. That's the total number. Now when we look at this one right here, that's here, A. It's separate from any of the others. Do y'all follow me? The next one is M Mexican. It'll be here. And the last one is G German. I'm trying to represent this in a Venn diagram. So that gives you an aerial kind of view of the probabilities of any of those occurring. You can see whenever we talk about probability of A occurring, right, in this possible event, it's just this number divided by the total number. This one would be the same thing, M, whatever that number is, divided by total N. And this is G, whatever that is, that number divided by total. So the total probability of getting a beer, single beer from all 5 beers from the same country would be the additive probability because they're disjoint. Do you all follow me? Now, if they were overlapping, then it wouldn't be the same. Then we have to subtract off the overlapped area. Do you remember that in Venn diagrams? So at least for this one, if we're going to get all 5 from the same thing, probability of all either German, American, or Mexican it's gonna be that number, 29 combination 5, over this number, 12 combination 5, plus 8 combination 5, plus 9 combination 5, and I don't know what that is off the top of my head. I did all these, but
0.0082.
is that right? 0.0082, but check it on your calculators if you don't mind. I wrote a function for this combination in MathCAD so I could just put the numbers down. I'm going to show you this in a second, and I put like, if I have 12 possible, 5, what's the combinations and permutations? I did them both, and I pull it out, and I can actually just put down that function in there and get them, and get the total number too. And is that right? So it's, what is that, 0.82%? Correct? What's the next part of that one?
That was it. for that
That's
first
all
two.
good.
All right, now I got a question for you. Since we're talking about beer and wine, something, at least some students are interested. All right, so for this one, what's the probability of getting 3 American beers and the rest, I guess, foreign or international, something non-American? How would you do that? Think about it. Think about this.
12 combination 3 plus.
Well, we know the total number of possibilities is that, right? If we take 5, and I want 2 or more American beers. Let's do it that way. 2 or more American beers. How would you do it? Well, I'd find first the total number of combinations, right? We got that there. Then I'd find what is the probability of just getting 2 American beers and 3, I guess, foreign beers, right? Plus the probability of getting 3 American beers times the probability of getting 2 foreign beers, plus the probability of getting 4 American beers and 4 American beers, 1 foreign beer, and finally the probability of just having all American beers. Do y'all hear me on this? I want to do this part for you and think about what I'm saying. So if I want the probability of getting 2 or more American beers, I'll just say A greater than or equal to 2 out of this 5 sample. Down here, we're still going to have 29 combination 5. Do this one with me. So now the first one is 2 American, 3 foreign, right? Hear me? So for American, we got 12, so it would be 12 combination 2, but it has to be multiplied by the probability of getting
17.
of 217, right? Or 17 2, correct? Now order's not important. With me, class?
Be combination
Sweet.
3.
Yeah.
I'm
Seeing the total is 5.
yeah, you're right. And then plus what?
12
Combination 3, and this would be 17 combination 2, correct? Plus, and then it's going to be, no, 12 combination 4, right? And then 17 combination 1 plus just what? 12 combination 5, and it's just 1 for the other one. Agreed? So what's that number? By the way, when you work this out, if you do every permutation, all American, 1 American, 2 American or more, and also just do it this way. If you have no American, 1 American, 2 American, 3 American, 4 American, 5 American, you add them up and stuff like this, now you get a probability of an American beer, and it comes out to be just the ratio of 12 over 29. But I'm not gonna, these things do work in terms of the final thing. Yeah.
84,007.
For all that stuff on top,
I put it over the, oh wait, sorry.
can't be, this is gonna be fractional. It's gonna be less than, I want you to do that because that's the kind of question that could come at you. Y'all with me on this? I'm trying to give you as many hints as I can because this stuff can get confusing. Okay. Say that again.
0.707.
0.707 for the whole thing?
Yeah.
All right.
Yeah.
Now, here's the thing. If you have the probability of no American beers and 1 American beer and add to that, you're gonna get exactly 1. Because that's 100% of the chance, right? You can either have none or all and everything in between. So when you add up the probabilities of all of those, you better get 1 or else you made a mistake somewhere. Y'all follow me in that? Did you have a question? Okay. But when I did this, I was trying to do Venn diagrams some way and show all these things, but sometimes it gets confusing, these things, especially when there's over. Are you with me on that, everyone? Okay. Now, next thing I want to talk about, talk something about conditional probability. I asked you to read that section, and we did combinations. We've gone through. In conditional probability, this starts on page 29 in my textbook. I don't know where it is on the PDF. But I want to just show you this with Venn diagrams because this will make sense to you. And then you'll start seeing, at least I think you'll start seeing a little clearer what goes on. Because sometimes when I'm trying to create all possible combinations and then circle the subset, it's just very hard to do it for me. All right, so now we're talking about conditional probability. It means given an event occurred, what's the probability of another event happening that's related? So we talk about this. First we have to draw the old Venn diagram. So if I have A and I have B, and I talk about the probability of the intersection of A and B occurring. Now think about this. I always talk about S is the total number of possibilities. It's related to that area there. What is the probability of this event occurring? Just follow me on that area. So there's 2 ways to do it. Well, there's several ways actually. So if I give you event B occurred, so B occurred. So I'm going to say, this is probability of B occurred. That's this area, if you think about it, right here. If B occurred, right there, well, wait, I'm putting this up wrong. I better do it this way. I'm sorry. If I want the probability of A given B, what this is the probability of A intersect B over probability of B. And I'm trying to explain this in terms of areas, the way I think of it. If they say B occurred, this happened. Now just think of the area of the probabilistic area, proportional to the likelihood of the probability, is now cut down from all S to this, right? This happened. So what's the probability of this happening? Is the intersection of the areas. This should make sense to you, does it? You follow me on that? And by the same token, if I looked at, I could say the probability of B given A would be still the intersection of A and B, but then it would be divided by the probability of A. Do you all follow me on that, class? So that's conditional probability in essence from a Venn diagram perspective. He has a lot more to say about this, and we're going to talk about this. We're going to talk about a lot of stuff. And this is on page 20. He shows this on page 31, what I just showed you. And he also goes through the law of total probabilities on page 35. Just hear me now before I go too far afield of this. Talked about some of the other things. And right here's a perfect, before I get into too much of this other stuff, he has a lot of discrete stuff here, but what I wanted to do is this. I'm going to use my laptop here to actually, I've got a PDF. Don't worry, I'll provide you the PDF. It was created by Tom Denny years ago, but it's, what happened to this thing? Somebody mangled this sucker. I don't know if this is gonna work, but we'll try. Is that HDMI or not? It'll help you. I think I got 2 minutes, right? Okay, and I'm sorry, and I apologize for this. Can you get those lights too, please? So when we talk about, everything we've talked about were discrete events and the possibility of them happening. So there's something called a probability density function that you're going to be exposed to. It really has to do with the frequency or likelihood of an event occurring over the total possibility of events. And let me give you, for instance, if we have a dice, just dice, we know we have 6 possible event or sizes that can occur, or 6 possible outcomes. And if we have a dice and we roll it, we can get 1, 2, 3, 4, 5, 6. So if we take a single dice and we roll it over and over and over and over again a large number of times, the probability of a 1 occurring is really going to be 1/6 as the event space gets large, tends towards infinity. We do an infinite number of rolls. That's if it's a fair die. Does that make sense? The probability of a 2 would be 1/6, and so forth. Now this I'm showing you after a large number of events what the likelihood is. What this probability of 1 really has to do with is the likelihood or the number of 1s rolled over the number of total events possible. That's all I'm showing you. You all follow me? It's really a frequency divided by total number of events, or how many times a certain event occurs over the total number possible. That's all that I'm showing you here. So the ratio of these two for discrete or continuous random variables, if we assume a large number of things occurred, in other words, that the dice rolling was a very large number, 10,000, 100,000, 10,000, it becomes something that becomes, it asymptotically approaches a steady state value. Now, when we talk about a probability density function, a PDF, what we're really talking about, if we look for dice, for instance, okay, and we had this the event of a 1, this the event of a 2, this the event of a 3 being rolled, 4, 5, and 6. The probability density function has to do with the probability of each one, or really the possibility of this happening. So for this one it would be 1/6, right? This one it would be 1/6. This one 1/6. You can see what I'm doing here. I'm just showing you a stem plot of 1/6 all the way down the line. Now, when you look at that, if you take a look at this being the PDF, this is for discrete, the sum of the PDF for all possible values, so I'll call it the PDF for I equals 1 to 6, has to be 1. The likelihood that something is going to happen, one of these events happens, has to be 1. Do you all follow me? This is a discrete probability density function that I'm relating to a dice being rolled a large number of times without getting in too much detail because I'm having a lot of time. Just let me finish this thought. So when we talk about continuous random variables, we say that now the outcome is not just in categories, 1, 2, 3, 4. It can have any value. And it's called a probability density function. This I'm very familiar with. It's called a PDF. So there's a couple of characteristics of a PDF. One is if you integrate from all possible values of a PDF of, and let's say its variance is x, dx, you have to get 1. That's the fact. Now what is a PDF? It's representing the likelihood or the probability of a certain event occurring, just like with the dice. And I'll try to show you what I'm talking about clearly. So over here, if I come back to this, and I'm stepping from that, from a discrete event to a continuous. If you take a look at a standard probability density function, it may look like this. This is a Gaussian curve. But this is the PDF of an event, whatever it is. I'll call it of x. And this is the probability of x having any value. So here's x, right? Y'all with me? Now one thing we know, the integration of that from minus infinity to infinity has to be 1. The likelihood of x having one of those values has to be 1. Now the probability that it has a value over a certain range, now I'm going to say it this way. This capital P means probability. The probability from a greater than or equal to x less than or equal to b is just the integration from a, I'm assuming a less than or equal to b, from a to b of the PDF of x dx. This should be intuitively obvious, all right? That's the probability. There's a lot of different things we can talk about. That's just the probability of event occurring. Now, if you talk about, and I'm out of time, if I talked about the probability of x having certain values given x is greater than a certain value, do y'all hear me? So let's say I want the probability, call this xa, right here. I want the probability of x having values like from here, call it xb, from here upwards, given it has at least this value. Now just listen to this part and you're gone. Got me on this? I'm saying x is at least this. It's given that it's this, right? At least this. Can't be this. Then it's really the area under that curve from x, because we want to know the probability that x is greater than some xb, given it's greater than, given xa, it's greater than xa. And this is that thing. Then it would be the ratio of this total area there to the area over there. And I'm going to get to that next time. That's what I was trying to do to show you how you have conditional probability for continuous time, or for variables that are continuous. And I'm so sorry this failed. I'm going to go talk to Dr. Nelms about this. I apologize to you. I thought this was a no-brainer today, or I'd have come down here on the weekends. I never had this happen in my life, and I've used this thing before. But they did something to this thing.